Welcome, everybody. The transition of energy is upon us, and there's a great need for people with the digital skills to become interested in understanding and enabling the energy transition that is currently picking up speed. There are orders of magnitude more complexity to decarbonized energy systems than there is to today's carbonized one. Without effective digital systems in place to instantly match that high degree of supply variability with the demand variation in real time, we're going to struggle. So my intention in these next 20 minutes is to give you a grounding in the global energy transition, the whys and the wherefores, and what it might look like in 2050 if we get it right. I will explain it through the lens of clean hydrogen, and I'm going to read this speech to make sure that I get it all the info in on time and you get what you need. So all energy transitions are messy. Lots of people think that all we need to do is put up enough windmills and solar panels and all will be well. And that is just not so. Solar panels don't work at night, nor work well in winter latitudes and in higher latitudes at winter. And they can suffer from long spells of cloudy weather and fire smoke, and wind might not blow for weeks in a row. And add to that, our weather patterns are shifting. They're not as reliable as they used to be. So low carbon hydrogen will actually help us to maintain energy on demand. And that means that when we flip the light switch on, the light comes on. And that helps us. Hydrogen helps us to keep from devolving into energy as available. So what does energy available look like? Well, I have a Polish friend, and one day we were chatting on the phone, and suddenly she got all excited because the power had just come on, and she didn't know how long it was going to be on for. So she hung up and rushed home to have a quick shower and then fill the bathtub with water for the family to use, hoping that it will last until the next time the power comes on. So you see, the water only came on when there was power to drive the pumps. That's an example of what energy as available looks like. And as we electrify more and more of our lives, hydrogen is absolutely critical to make our renewable energy systems more dependable, more reliable, resilient, robust, and less messy, and preserve energy on demand that we're used to. So we're going to start with hydrogen basics, and we're going to build from there. As you know, hydrogen is the smallest element we have. The red arrow points to its location on the periodic table. We generally write the chemical formula for hydrogen as H2, and that's because it always shows up with two hydrogen atoms bonded together into one molecule of hydrogen. The energy in a hydrogen molecule is actually stored on the hydrogen bond right between the two atoms. It's marked by the purple arrow here. When we break that bond, energy is released. This is what hydrogen looks like in the universe through a telescope. This is actually a nebula. About 73% of the mass of the visible universe is in the form of hydrogen. And about helium makes about 25%, and everything else we know and love is only about 2%. However, there's no free hydrogen on Earth. Most of the hydrogen we have is tied up in ocean water. So we have to make it. And hydrogen is therefore not an energy source, it's an energy carrier. So our challenge today is that 95% of the world's energy system is based on hydrocarbons, coal, oil, and gas, which are made of, you guessed it, hydrogens and carbons, hence the word hydrocarbons. Here are some hydrocarbon chemical structures. The first three molecules represent in order coal, oil, and natural gas. And you can see that there's a lot of carbon atoms in there. When we burn these for energy, we poop that CO2 off into the atmosphere. But where does the energy actually come from? Mostly, again, from the hydrogen bond itself. When we break that hydrogen bond by burning hydrocarbons, we release heat for our use. So why hydrogen? It's shown in the red arrow, because there are no carbons at all in hydrogen. So when we break that hydrogen bond for energy, no CO2 results, only water, H2O, and that is why hydrogen. So why is the world moving away from hydrocarbons then? Well, because of the unintended consequences of climate change and weather weirding that results from that. This pie chart actually shows you the percentages of warming caused by the various greenhouse gases currently overheating our atmosphere. And the lion's share of excess greenhouse gas effects, it's from CO2, that's from burning fossil fuels. 62% of the total. That's the biggest blue pie slice on the right. And we have learned two things, really, that affect everything in our lives. And one is energy and one is climate. And the two are absolutely intimately related. So here's the kicker, though. Only 20% of that big blue pie slice is CO2 released by oil companies making fuels for us. And 80% is actually released by us when we burn that fuel to use it through our tailpipes, our home chimneys, and our industrial stacks. So how does CO2 work in the atmosphere anyway? Well, here it is in a nutshell. Our planet has a natural blanket of heat-trapping gases in the atmosphere, which is dominantly CO2. This natural blanket keeps the Earth at about 30 degrees Celsius warmer than it would be otherwise. It's natural. Normally, sunlight comes down through the atmosphere and goes through the atmosphere like a window, and then it hits the Earth, and that changes it from light to heat. That is a change from shortwave to long-wave radiation, which is then reflected back up into space, but some of the heat gets trapped in the atmosphere by heat-trapping gases like CO2 or methane and others. It works just like a blanket that traps your body heat in on a cold night. So what's the problem? Well, the problem is by digging up and burning oil and coal and natural gas, which release large quantities of CO2, we are wrapping an extra blanket of heat-trapping gases around the planet. And just like you would if your grandma snuck into your room at night and put an extra down comforter over you, you would wake up sweating too. So in the same way, our Earth is extra hot because of this extra blanket we've wrapped around it. And we're trying to keep our planet under 2 degrees Celsius of extra atmospheric heating, which doesn't sound like much, does it? Some of us might think, well, what's the big deal with that? You know, if the air temperature goes up by 2 degrees around me anyway, so what? But it doesn't work that way. That is weather. Climate, however, is the average of all weather everywhere over the past 20 to 30 years. Climate change acts more like a chronic fever in your body. If your body ran a 2-degree chronic fever of, say, 39 degrees Celsius, you wouldn't be operating very well either. So, what can we do about our changing world climate? Well, we can decarbonize our energy use individually and collectively by making different choices. Fossil fuel vehicles are going away. What will replace them? Well, my rule of thumb is if a vehicle currently runs on gasoline, it's better off going battery electric. And if a vehicle runs on diesel, it's better off going hydrogen fuel cell electric. And electric cars are more fun and cheaper to drive anyway. And I know because this is my 2013 Tesla S85, which I bought used, sitting beside our garage with its solar panels on it. And those solar panels partially power the car in my house. So what's the problem giving up oil then? Why is it just so dang hard? And so here's a question I want you to come up with an answer to. How many human work hours do you think are in a single barrel of oil? Go ahead, take the next 5 seconds and pick a number in your head. 3, 2, 1. It's 4,053 human work hours. That's 2 years of 40-hour work weeks. At $15 an hour, a single barrel of oil is worth $61,000. And we pay what for that? You know, $80 a barrel. This is a hard thing to replace. It is critical for skilled digital workers to understand this complexity of what we have to do. So what might the clean future for global energy mix look like? Well, here is our palette of renewable, low carbon energy choices that we have to work with. And we have to put them all together to replace hydrocarbons. These are real, like they're happening today. These are real pictures of real projects. Here's what they look like. And starting in the top left corner, moving right, we have hydro dams, wind farms on land, wind farms in the ocean, solar farms on land, and also floating solar on lakes and irrigation canals. Geothermal, biomass that makes either fuel or power, wave energy, tidal energy, waste to fuel or power, blue hydrogen from natural gas with carbon sequestration, capture and sequestration, which is CCS, and then green hydrogen, this one from a solar farm. And we'll talk about nuclear, which is key, a little bit later. So to reiterate, we're going from 95% fossil carbon-based energy on this planet in red to a low carbon energy sources and carriers, which we have just reviewed in blue. And now we're adding another level of complexity, which is energy storage in green. Our problem is electricity does not store at all well, especially at large scale and over seasons or years, which is what we need it to do. We just can't make batteries big enough. So as an example, this is Elon Musk's $40 million worth of batteries, 100 megawatts in South Australia. And it is used to balance the grid by keeping the frequency content steady so the grid doesn't crash, right? Which it does remarkably well. But if it were to actually power the grid, it would last about 7 minutes. That's it. So other methods of electricity storage are absolutely vital. These include pumped hydro and flywheels and compressed air or liquefied air too, supercapacitors, grid to vehicle storage, and gravity, which is one of the weirdest in my view. This is what one version of a gravity electricity storage system looks like. So when there's more power supply than demand, we can use that excess power to lift a heavy weight into the air to store the electricity as potential energy. And then when we need that power back, we just lower the weight and harvest the kinetic energy as electricity. So electricity can also be stored as heat. Molten salts, hot rocks, and storage in ground heat storage are just some of the options. Best of all, electricity can be stored as hydrogen. And so how the heck do we actually make hydrogen on this planet? Well, this bar chart shows all the ways we have for making hydrogen, each of which is referred to as a color in the industry. The life cycle carbon intensity range on each bar expresses the number of kilograms of CO2 that's involved in making 1 kilogram of hydrogen. But what does life cycle carbon intensity really mean, really? For example, let's use solar panels. The solar panel carbon intensity numbers include mining of the elements that are in it, concentrating those elements, purification of them, then transportation to manufacturer, then the manufacturing of the panels, packaging and transportation to market. The CO2 released in all of that per kilogram of hydrogen made over the lifetime of the project is what life cycle carbon intensity means. And that is actually what matters. So today, 95% of all hydrogen we make is gray and brown, shown by the last 2 bars on the far right. The gray bar, second from the right, is gray hydrogen made from methane and water, while pooping the CO2 off into the atmosphere. It releases somewhere between 9 and 13 kilograms of CO2 per kilogram of hydrogen. On the farthest right, in brown hydrogen is made from coal, which poofs off about 15 to 25 kilograms of CO2. These are both very high. So notice the orange line now. At the 5 kilogram mark, anything below that line meets the European Union definition of low carbon hydrogen, which is where you want to be, below that line. So we will talk about the lowest three of the hydrogen production types on the left. The lowest carbon intensity is pink hydrogen, made from nuclear, used to split water. By electrolysis, it's 1 to 2. Next over is green from wind and solar. I've added them together here. Wind is about the same as nuclear, a little higher, but about 1 to 2. And solar is higher, though, at 3 to 4. Next over is blue hydrogen from methane and water and using 90% carbon capture and sequestration. And it comes out at 2 to 3. But if we include the fugitive methane emissions that escape from the natural gas supply chain, then it's about 2 to 4. So notice all of these first three bars are less than the orange line and therefore are all defined as low carbon hydrogen. So now that we know how to make clean hydrogen, what are we going to use it for? Well, today most of hydrogen is used for 4 things: oil refining, ammonia for fertilizers, methanol, and as a feedstock for petrochemical products like plastics. And all of these can be done with low carbon hydrogen just as well. So what else are we going to do with it? Well, on this slide, highlighted in yellow, are the other uses best done with hydrogen and not electricity. These include powering fuel cells to provide heat and power or backup power to commercial and public buildings. Energy system management means storing hydrogen as seasonal energy backup. Industrial processes includes, for example, using hydrogen for steel and cement making. Heavy long distance transportation of all sorts, plus agricultural machinery. So what might the world's energy mix look like by 2050? And if we get it right, and this is just my best guess as of today, and all of it has to work seamlessly, connected to the Internet of Things, and have robust digital management protocols. By 2050, we will be electrifying everything that we can and powering it with renewable, clean electricity, somewhere in the range of 55 to 70% of our world energy needs. And we must double or triple the size of our current electric grids, while at the very same time changing over from high carbon power sources to low carbon power sources. And nuclear capacity is absolutely key. We will need to at least triple our current 11% of grid capacity that is provided by nuclear to about 25 to 40% in this larger grid. Low carbon hydrogen will actually be key stabilizer of the whole thing. And backup as a backup and storage medium, in addition to running heavy vehicles and industrial heat. But it will be the second most used form of clean energy at about 35 to 45%. Biomass will be much smaller, with fuels derived from plant wastes and garbage dumps and poop, totaling 4 to 8%. Now, my guess is that hydrocarbons will form less than 25% by 2050, and over half of those will likely be combined with carbon capture and storage, so their emissions won't be significant. On top of that, we absolutely must eliminate 30% energy waste, which is what we've got. We waste a lot of energy in developed countries. Everybody's house wastes an average of 30% of the energy that comes into it. By eliminating that waste and other wastes, we will have enough energy to both serve the additional population that will be here on the planet by 2050 and lift most of the people out of energy poverty. And lastly, we need to put effort into ongoing atmospheric carbon dioxide removal. And that means continuously pulling CO2 out of the air and storing it permanently in the ground. And we can also sequester carbon dioxide and carbon black as biochar and other things in soils and forests and managed tree farms. So every country and region in the world will have a different combination of the solutions that I've put forward that all need to be knit together in different ways. The analogy it's like painting a picture. So every country will paint their own clean energy picture according to their own resource endowments, their needs, their financial strength, and their social adoption. My job as a technology scout is to make sure that the technology is there, that all the colors are there. So the palette of colors are affordable, and every country has a full suite to choose from, depending on their own circumstances. Your job as skilled digital knowledge workers is going to be the paintbrushes here, to mix those colors, to apply them in a way that connects everything together and cover the entire canvas. Every country will envision and paint its own picture, and they will all be different. So lastly, I want to tell you about my pet project. There is so much good stuff going on in the world today to actually address climate change, and we never hear about it. No wonder people, especially kids, are feeling hopeless. And if you want to know about it, consider signing up to my Patreon, to be a patron on my Patreon blog page, which is called How the Future Can Go Really, Really Well. Get 2 positive articles by email in English every morning, 3 on the weekends. I aim for a grade 10 level of understanding. I don't always hit that, but I do that so your kids might find hope in it too. So now you've had an overview of the energy transition, and so you can ask yourself if this lights you up or not. And if it does, I hope you will consider applying your digital skills to help make it happen. In the future, if we get this right, the light will still come on when you flip the switch, but what is behind the scenes will look very different. Feel free, as you choose, to connect with me on LinkedIn or follow me on Twitter and become a patron of my blog, or email with any further questions or ideas you may have. I am also happy to have my brain picked anytime. Happy to help. Thank you for your kind attention, and I would love to answer your questions anytime.